Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And today we're going to take a look at how we find the tangent line of a curve defined by a polar function. So here we're looking at the graph of a polar function, r equals 2 plus 3 sine theta, and the shape of this graph is called a limacon, and you see it has an outer loop and an inner loop to it, and you can class it as a part of the cardioid family, and you can classify those by the coefficients and whether it's a sine or cosine function. But anyway, if you have a polar function graph where you can get a good look at that thing, and we're looking at it, the assumption is we're going from 0 to 2 pi when we see these polar functions in the, for the most case anyway. So what we're trying to do is to find the tangent line slope at 0.2 pi. We got to be a little careful here because when we're talking about coordinates in polar form, it's not x, y. We're talking about r theta as our ordered pair. So we're talking about a rotation of theta. I like to think of it as backwards almost. Do the rotation of theta first from standard position, which would be the negative x-axis, and I have a radius of 2, which means my point is right here. So depending how we're describing that, if we're in polar coordinates, that's 0.2 pi. And if we would convert that into rectangular coordinates, then we would find that that is -2, on the Cartesian plane. And that could be actually determined this way. We don't need to do all the details at the moment, but the key to understanding the calculus, the derivative of the polar function, is that how do we convert between polar and rectangular coordinates? And this goes back into the vectors and everything else. So the fact that, and even like the trigonometric functions of any angle, which sometimes we call those the x, y, r definitions. So if you go back to trig class, you say, well, the cosine of theta for any angle is x over r, so that means that x equals r cosine theta. And the sine of theta is y over r, so that means that y equals r sine theta. So I could take my coordinates at 2 pi and convert those over and say, well, then x is equal to 2 times the cosine of pi, which is 2 times -1, or -2, and then y is equal to 2 times the sine of pi, which is 0. So depending how you would want to describe that point, you could do it in either the r theta or the xy. So that's kind of the pre-calc of it. But it turns out that those definitions have a lot to do with finding derivatives as well, because what we're trying to do here is determine the tangent line slope on our polar graph here, dy dx. And the way we do that is to go back and think of the polar function parametrically. And to convert a polar function into parametric form, all we really need to do here is to apply these definitions. X equals r cosine theta and y equals r sine theta. So if I go ahead and do that, that means that my x component here in parametric form is going to be r, which is the function itself, 2 plus 3 sine theta, times the cosine of theta, and then y is equal to 2 plus 3 sine theta times the sine of theta. So there we have r cosine theta for x, r sine theta for y. That means then that x is equal to 2 cosine theta plus 3 sine theta cosine theta. And then for y is equal to 2 sine theta plus 3 sine squared theta. So I went ahead and actually did the conversion from the polar equation into its parametric form. So if you have your calculator out, you might want to actually go ahead and confirm that that all works. Go from your parametric mode and type it in this way, and then go back into your polar form and put in the original function. But this is what's all behind this big scary looking formula that defines the derivative of a polar function. But if you understand what's going on here, it makes perfect sense. It says that the tangent line slope dy dx is equal to the first derivative in parametric form, which is dy d theta over dx d theta. And dy d theta is done by a product rule of r times the sine of theta. So if we look at the numerator of our formula, then that would be r times the derivative of the sine, so r cosine, plus r prime times the sine. So it's just the product rule of r sine theta. And then the denominator of our derivative in polar form is the product rule applied to r cosine theta. So the derivative of the cosine is negative sine, so that's where we see this minus r sine theta first, plus r prime cosine theta second. So like a lot of other things in math, if you want to go ahead and memorize that formula as the derivative of the polar equation, that's all well and good. Personally, I just like to go ahead and define x and y in their parametric form, and then we just go ahead and do the derivative parametrically. So then I would be doing this part of it and saying, okay, well, now I'm just going to calculate dy d theta over dx d theta, which can still be kind of messy. However, what do I need this for? All I have to do is be able to evaluate it at the end of the day at polar coordinates 2 pi. So that's how I'm going to do it, my recommendation. And so if we look at y, dy d theta here, so y is 2 sine theta, 3 sine squared. So dy d theta is 2 cosine theta. And I have a little chain rule there, so plus 6 sine theta times the cosine of theta. So that's dy d theta, without memorizing any formulas. And then dx d theta would be negative 2 sine theta. And I got a little product rule here, so it's going to be 3 sine theta times negative sine theta, so minus 3 sine squared theta, we'll call that, plus 3 times cosine, so plus 3 cosine squared theta. So sometimes you may be able to clean it up a bit here. There actually is no common factor or anything worth going after, I would say. So, but we do have some kind of a function of theta that will define the tangent line slope on this Limousin curve for anything between 0 and 2 pi. So all I need to do now is plug in theta equal to pi and evaluate that. And so we see here that we get 2 times the cosine of pi, which is negative 2. Anywhere where you see a sign now, this is going to be 0. Sine of pi is 0, so negative 2 plus 0 divided by 0 minus 0. And then here we have cosine squared, so that's going to be a plus 1, so plus 3. And we see that our tangent line slope there is negative 2/3. So we defined by converting the polar function into its parametric form, which is as simple as r cosine theta, r sine theta, and then doing the parametric derivative, we've come up with a function that defines the tangent line slope as a function of theta on this polar curve. And we could do anything we want from that point on. So, for instance, if we're asked for a tangent line equation, typically when we go to lines, we don't often define lines in polar form. We usually go back to the rectangular coordinates. So let's just say I wanted that tangent line equation. Do a little point slope form on that. Y minus 0 equals negative 2/3 x plus 2. So my equation there is y equals negative 2/3 x minus 4/3. So the polar equation derivative formula, it's a scary looking thing if you just look at it in the textbook, but if you really take a minute and understand what it is and what it's saying, it's not that difficult. Don't be intimidated by the trig functions in there. Just go ahead and follow the rules, and everything usually works out pretty well with those. So my advice to you, define this thing parametrically and just do the first derivative as a parametric derivative. That seems to be the easiest way out. If you'd like to learn more about the calculus of polar functions or calculus in general, you can find that information in my textbooks available on Amazon for a nice price. Don't forget to subscribe to the channel if you like it. And until next time, I'm Pete Clark.